In this ninth session, we are going to learn about design parameters. Okay. So this is our model. We have prepared this model. Okay. So to assign our design parameters, we have to go to our design tab and then steel. Okay. We have two types of design parameters for steel and concrete. Okay. So as we are designing, so here we are designing our, designing this shade at AC, sorry, uh, AISC, okay, 360.05, okay. So this is our design code, okay. This is our design code, okay, for steel. For RCC, we are going to design according to ACI 3180. So this is our specifications for our course. Okay. So we are going to design three. Okay, that's fine. So we just clear this one. So just go there. Okay, you can see AISC 360. Okay, 5. Okay. Okay. Then you can see here we have a defined parameters and we have commands. Okay, so we will go to command, not now. We will go to define parameter. You can see we have a lot of parameter. Okay, but we will discuss and assign those who have a great impact on design. Okay, so I have prepared a sheet for you. You can see here. Okay, you can see. First of all, okay, we will assign, okay, first of all, we will assign this parameter. This is FYLD. What is the meaning FYLD? This is the yield strength of the member. Okay, so go to parameter tab. Here you can see this is FYLD. Okay, by default, you can see here by default there is a value. Okay, this value equals to this value equals to this value equals to, okay, equivalent to 36 KSI. Okay, that means this is 36 grid. Okay, but we will design our shade as per 50 grid. Okay, so we need to change this value. Okay, so to do that, so 50 grid. Okay, as we are designing our members as 50 grid, so the value will be, okay, this is our value for 50 grid in kilonewton per meter square. Okay, then add this one. Okay, second we have to go ultimate strength. If you go here, this is our ultimate strength. Okay, ultimate strength. Okay, so just keep in mind that. Okay, so Fy Fu. Okay, so for 36, if u equal to 80 KSI. Okay, for 50 grid or 50 KSI, this value will be 65 KSI. Okay, and convert this 65 KSI to kilonewton per meter square, and then you can put, okay, and then go to our model, and then you can put probably 382. Okay, 382, and then just add this one. Okay, so now go to our so here we have the value. So what is the value? So for 40 grade, so sorry, for 50 grade, we have 345 kilonewton per meter square. And we have FU, ultimate strength, that is 4, 4, 8 and 382 kilonewton per meter square for 50 grade. Okay, for 50 grade steel. Okay, so these two values are very critical, for the design of our shape. Okay, now what is the method? Okay, so AISC have two methods, ASD and LRFD. Okay, so here we are going to design our members as per LRFD. Okay, in software the value is as default ASD. Okay, so we go to our model again. Here you can see we have method. Just click LRFD and then add this one. Okay, so here you can see, again we go to our document, and this was also, sorry, and this was also done. So these three has been done. Okay, so now we have UNT. So okay, what is UNT? Unsupported length at top flange. Okay, and what is UNB? Okay, unsupported length at the bottom flange. So what is UNT and what is UNB? You can see from here. UNT is the spacing of purling. Okay, spacing of purling. And what is UNB? UNB is the spacing of flange brace. Okay, so if we go to another figure, you can see, if I go here, okay, you can see here, you can look at this figure. Here you can see, this is our purling. Okay, this is our purling. Okay, so distance between this purling will be UNT. Okay, and here you can see there's another member here. This one, this one, this one, this one, or maybe this one. So these are called flange brace. What is called? Flange brace. Okay. It's called flange brace. Okay. So you can see the distance of flange brace is called UNB. Okay. Similarly, for column, this for for rafter, for column. Similarly, here you can see there is also a purlin, but this purlin will be termed as guard. Okay, guard. When purlin is connected with column, then it will be called a guard. Okay, and you can see this is guard. So the spacing between two guard, okay, will be termed as UNT. Okay, here you can see there is a member. This is also called flange brace. Flange brace, and this is connected with another, flange of the column. So this guard is connected to one. Here you can see connected to one flange of a column, and this guard, okay, sorry, and this flange brace is connected to another, okay, flange of the column. So this is a flange brace, and you will get the value of UNB from flange brace here. Okay, So this is how you can find out UNT and UNB. Okay. So for our case, we consider our purlin spacing. Purlin spacing for our case for rafter is 1.2 meter. Okay. And flange brace equal to, for now we are just going 2.4 meter. Okay, so we will consider our flange brace will be alternate. So our flange brace will be here, not here, and after here. So alternate of a purlin. So 2 times. Okay, you can assign 1.2 here. Okay, this is only up to you how you are going to design this one. Okay, so for initial start, we are going to start with this 1.2 meter and flange brace at the rate of 2.4 meter, because we will provide our flange brace at alternate purlin. Okay, so we go to our model. So this is our, we can go to UNT. Here is the UNT. For our case, it is 1.2. Okay, if you don't apply 1.2, software will automatically consider the default length of the member. Okay, so at this one, this is for rafter, and UNB it is 2.4, as we are considering alternate purlin. Okay, so the purlin, so the flange brace will stay after each. Sorry, we will stay after alternate purlin. Okay. So at this one, probably I have added 2, so I just check it. Okay. Okay. So, okay. So here you can see, if we go to our parameter, so for our cases, the value is 1.2 meter, and for this is 2.4 meter, as we are considering at the rate of alternate purlin. Okay, so what is STP? You can go here. You can see what is STP. You can see this is the type of the member. Okay, 1 for roll section mean hot roll, and 2 for welded section mean build up section. So here we are modeling as for build up section, so we'll assign this as 2. Okay, just add this one. So here you can see, you can go to your parameter, so the value will be 2. Okay, as we are designing for build up section, you can see we are designing for build up section. Okay, so what is UNT? UNT is the spacing of purlin. What is UNB? And UNB is spacing of spacing of the flange brace. Okay, here we have considered flange brace at alternate. Okay, purlins. Okay, so what is CB? CB is moment gradient factor. Okay, what is CB? CB is called moment gradient factor. Okay, by default, the value is 1. Okay, by default value is 1. Okay, so if we go to our model, you can go to CB. Okay, you can see 1. By default it is 1. Okay, we will put here 0. Okay, we will put here 0. Okay, now we just want to see what is CB. Okay, so this is the equation of, here you can see, this is the equation of CB. Okay, you can find it from AISC. No, AISC, you can find it from AISC, any version or any book. Okay, so this is the equation of CB. Okay, so in Stadd Pro, CB is always 1 by default. Okay, so if you put CB equal to 0, so then software will calculate. Okay, then software will calculate the actual value of CB. Here CB equals to 0 means not 0. 0 means you are telling software that you calculate. Okay, so that's why we have put 0 here, and then we will add here. Okay, again we go to our design parameters, so we will put a 0. 0 means software will calculate. Okay. So here you can see there is another parameter which is very, very important. LX, LY, and LZ. Okay. This is LX, LY, and LZ. Okay. So first of all, we will start from LY. Okay, we will start from LY, LZ, and then we will go to LX. So first of all, what is LX? You can see length to calculate slenderness ratio for buckling about Y axis. That means this is K, sorry, this is KL by R. Okay, clear? So you have to provide this LY or LZ to the software for any particular member. Okay. So here you can see if we go to our model, here we can see if we go to LY or LZ. Okay, if we go LY, you can see default length is beam or members length. Okay. So now we go to model. We go to model. Here we can see. Here you can see this is a column. The column is not broken anywhere. Okay, it starts from here and ends here. So column is not broken anywhere. Okay, you can see column is not broken anywhere. So software will automatically calculate the unsupported length. Okay, software will calculate automatically the unsupported length as the column is not been broken anywhere. But in case of rafter, here you can see the rafter, the total length of the rafter is this one. Okay, 29.61. But the rafter is broken. Here you can see in multiple, in multiple, spacing. Okay, here you can see first part, second part, third part, fourth part, fifth part, and sixth part. This is the total rafter, but rafter is split. Okay, so you have to assign right LY and LZ so that model can find the LY and LZ to calculate slenderness. Okay, so we will not save now, we will save it later. Okay, here you can see. Okay, we have not modeled, purlin and flange brace. We will not model because we don't need model of purlin and flange brace, but we will consider their effect in our model. Okay, so to do that, okay, so what is LY? So you have to go to another figure from design guide of Stadd Pro. Here you can see this is our LY, and here you can see this is LY. Now, what is the distance? This distance is LY. Okay, and what is LZ? This distance, here you can see this distance is our LZ. Okay, so our purlin is going in direction. Okay, this direction. Okay, this is connected with the top flange of the rafter. So this is LZ. Okay, LZ. And any member, I change the color. Okay, you can see any member going through wave. Okay, will be termed as LY. So in our cases, we have a start here. Okay, we have a start here. If we go to the model again, you can see if I extrude, sorry, if I extrude this, if you can see, if you go here, you can see here our start member is connected to the wave of the member. You can see. So if you compare this scenario with this figure, that you can find out, so this length and the spacing of this length will be termed as Ly. So for our cases, what is Ly? Okay, maximum spacing of start. This is called Ly. Okay, and what is Lz? Okay, Lz you can find out. Lz equal to maximum of UNT or UNB. Okay, so for our cases, our UNT was 1.2 meter and UNB was 2.4 meter. Okay, so Lz equal to 2.4 meter. Okay, so Lz equal to 2.4 meter and Ly, this is Ly actually, this is Ly equal to maximum spacing of starts. Okay, because purlin is going through here at the top of the flange, and flange brace, you can see flange brace is connected like this way. Okay, so this is Ly and Lz. So if I go to our document, you can see what is Ly, maximum distance between starts. Okay, and what is Lz? Lz is maximum or of UNT or UNB. So in our cases, our Lz equal to 2.4 meter and Ly equal to spacing of start member. So we just check from our model. We can go. You can see spacing from here to here. Okay, maximum spacing. So I think same. So 14.845. Okay, so we have 14. So we have 14.845. I just go to the model. No, or not 874. Okay. 874 meters. Okay, so this is our Ly and Lz. Okay, so now we just assign value. Again, define. So what is our Ly? Ly is 14.874 and Lz equal to 2.4 meter. Okay, so 2.4 meter. Okay, now we will also assign Lx. Lx is critical, you know, for unsymmetrical section. Okay, so we don't have to assign Ly and Lz for column because column is not broken anywhere. Okay, if the column is broken anywhere, you have to assign Ly and Lz or Lx for column 2. Okay, just remember this one. So what is Lx? Lx is similar to Lz, but then what is the meaning? Here you can see Lx means length for flexural torsional buckling. Keep it in mind, flexural torsional buckling. Okay, Lx represents flexural torsional buckling, whereas UNT and UNB, okay, both represents what? Lateral torsional buckling. Okay, So UNT and UNB represents lateral torsional buckling, whereas LX represents what? Flexural torsional buckling. Both are different. Okay. So what is LX? LX is similar to LZ. Okay. Maximum of UNT and UNB. So we have again LX equal to 2.4 meter. Okay. So then we go to our model. Then LX 2.4, sorry, 2.4, and then add this one. So this LX, LY, and LZ we are assigning for actually rafter. Okay. Because we don't have to assign for column because column is not broken, but rafter is broken, in multiple spacing. Okay. So again, we go to our next item. Okay. Here you can see we have also KX, KY, and KZ. Okay. So these are the value. So we will put 1, 1, and 1. Why? Because we are going to analyze our model as per direct analysis method. Okay. As per direct analysis method, we are going to analyze this model. Okay. So this is our direct analysis method. For direct analysis method, Kx, Ky value will be always 1. Okay. So our value will be 1. Okay. Another thing you have to note, default value for software equal to 1. Okay, similar. So if I go to Kx, Ky, or Kz, here you can see default is 1. Default is 1. So we don't have to assign this value because even if we don't assign Kx equal to 1, software will automatically put 1 because it is a default value. Okay. So we will not assign. Okay. Because it will automatically be assigned as 1. Okay. So let's go to again. Now there's another parameter. Okay. This is what is called. This is called main. Okay. If you go to AISC, okay, if we'll find allowable ratio, allowable KL by R ratio for flexural members, sorry, for compression members, equal to 200. This is as per AIS, you can see 200. Okay. For any compression member, KL by R ratio is maximum 200. Okay. Up to 200, it is allowable. Okay. If it is more than 200, then you have to, increase your size of the member. Okay. So this is a default value. You can see default is 2000. Okay. If you don't change, then 200 will be assigned automatically. Okay. So to do that, if we go to our main again, okay. So there is another value. There is another value you can see if I go to the document. There is another value. You will find it. It is T main. Okay. So main was, what is main? Main was for compression members. Okay. And T main is for tensile member, but on tension member. Same. Tension members, but allowable limit is 300. This is also as per AISC. Okay. So for compression members, KL by R equal to 200, maximum allowable 200. This is 200. Okay. For tension member, the allowable value is 300. Okay. So compression member is critical. So if we go to the model, here you can see if we have main here, you can see 200 is by default. Okay. So we will not assign because 200 will be automatically assigned, okay, to the member because it is a default value. Okay. So we will not assign is here. Okay. So this is our parameters, you can see. Okay. Now we will assign this parameter to the members. Okay. So first of all, okay, select this one. Okay. Select all the members except RCC members. You can see all the members. Select and then assign. No, assign to selected name and then yes. Okay. Again, go to selection. Don't assign in RCC part. Okay. Only still part. Assign. Okay. Now method is also assigned. You can see the tick mark here. Okay. UNT. Okay. Now this UNT is for rafter. Okay. So select all the rafters. Here you can see. Here you can see. This is this one rafter. This one is also rafter. This one is rafter. This one is rafter too. So we will assign this. Sorry. Select. So this is our rafter. You can see all the rafter has been selected. Just assign here. Okay. Again, this will be also assigned to the rafter. Go to selection, property name. Okay. And then assign. Okay. HTTP. So select. So this one, these are all, prefabricated or build up member. Okay. So just assign this one. Here you can see start, in our cases, our start was a, pipe section. Okay. So normally pipe section is, hot roll section. So we will not assign our, this one to, we will assign only column rafter. Okay. So just assign this value. Okay. CB. Okay. We will have to assign CB X to all the member except our bracing. You can see we have deselected our bracing. Okay. Okay. Then assign this one. Okay. So we have a problem. Just delete this one. Okay. And LY and LZ. Okay. So here you can see now we will assign LY. Okay. So here you can see, if we go there, here you can see for this rafter, okay, for this rafter, here you can see there is a start member. Okay. So for this rafter, the LY value is this one. Okay. So here, the model, the rafter is broken here. So by default, software will automatically calculate this length. Okay. So we don't have to put this for rafter, but here you can see, we have a total but here you can see the software will automatically calculate this one. Okay. For LY, but the actual LY is this length, because actually there is no start member here. Start member is here, but start member is not continuous here. For this rafter, the default length is okay, but for this rafter, the default length is not okay. So we will have to tell the software to change LY and LZ. So for this reason, you can see we have applied this length. So if we apply this, this, you can see. So several lengths. So these are the rafters. Okay, there you can see these rafters. Okay, we will not select these ones because the software will automatically calculate, this length because this is already their default length. But in case of this, software will calculate this one as their default length. But actually, start is here. So we'll have to assign the value to tell the software the actual length of Ly. So there is a missing one. Okay. So yeah, sure. Everything has been assigned. So just assign our Ly. Okay. So this is you can assign Ly. You don't have to assign Ly here because our start member is here. So you can see our default length is similar to our Ly length. So we don't have to assign Ly. But in this, for this rafters, our default length is not equal to our Ly. Then we have to assign this Ly. Okay. So now, we will assign LZ. So for LZ, we'll select all the rafters. Okay. Go to selection and then this one, this one, this one, and this one. So all the rafters and then, sorry. This one, this one, this one, and this one. Okay. Just assign. Again, LX, same. We will assign all the rafters. This one, this one, this one, this one. Okay. Okay. So parameters has been assigned. Okay. I will go to command. We will go to check. So there is another thing we have to assign this check code. Okay, just add this one. So check code will check according to the AISC code. Okay, so if you don't assign this, then you will not get the design. Okay, so select all the member except the bracing. Okay, because you can design bracing, cable bracing, or rod bracing here. So don't give it. Okay, so you can see our all the design parameters has been assigned. Okay, so we just recheck. Okay, so this is the yield strength of the member, and this one is the ultimate strength of the member, and this is our method. We are designing this. Okay, we are designing this. Okay, so just select all the members here. Let's see. So So this is our yield strain, this is ultimate strain, and this is our method, and this one is our UNT for rafter. Actually, what is UNT? UNT, the spacing of purlin. Okay. And what is UNB? UNB, the spacing of flange brace. Okay. So if you don't have any flange brace, then you will not get this UNB. Okay. So what is STP? STP actually tells you whether the section is hot rolled or built up section. For 2, it is a built up section. What is CB? CB is moment gradient factor. Okay. So we'll put 0, and 0 means software will calculate the actual CV value and assign through their equation. Okay. So what is LY? Okay. Again, we go there to our document. What is LY? LY is, LY is the length to calculate slenderness ratio for buckling about local Y axis. So we have shown you a figure. This is a figure. The member is connected through wave. Okay. The member is connected through wave, and then the spacing of those members will be termed as Ly. What is LZ? LZ, the member connected through flange or top flange or bottom flange, and then the spacing between those members will be termed as LZ. Okay. So always keep the figure in mind. Okay. You just have to check whether the member is connected to flange or wave. If it is connected to wave, then Ly you have to assign, and if it is connected to through flange, then you have to assign Lz. Okay. So then we go to another value, Lx. Lx is what is Lx? Lx, you can see here, Lx is the flexural torsional buckling length for flexural torsional buckling length, which is equal to Lz. So you can put the value of Lz here. Okay. Here you can see Lz equal to, what is Lz equal to? Maximum of UNT or UNB. Similarly, Lx equal to maximum of UNT or UNB. Okay. So Lx is critical. So Lx is critical for unsymmetrical section like T or C channel. Okay. So for for unsymmetrical section, L is very critical. For symmetrical section, L is not too much of critical. Okay. So keep that in mind. So then we have Kx, Ky, and Kz. Okay. These values are simply 1, because we are going to analyze our model by direct analysis method according to the stability. If we analyze any shade or any building through direct analysis method, then Kx, Ky, and Kz value will be 1, simply 1. Okay. For main, okay, for main we have a allowable value of 200. Okay. By default, software will give 200. Okay. Sorry, software will check whether any member has allowable compression ratio above 200. So there is another thing you can if you can look after. The thing is that, okay, so if say if you don't have, say, if you don't have this start, okay, say I will, okay, say, then what is the length of Ly for this rafter? Okay, the length will be the total length, this one plus this one. That means 29 point, most probably 29.6. I just check. Okay. So this value is, so what is the value? If we sum up, okay, if we sum up, then the value becomes 14.874 plus 14.874, which is equals to 29.7 4.8. Okay, then you have to assign Ly as 29.784. If you don't have this, if you don't have this start member here. Okay, so but we have the start member, so our Ly is okay. So we just undo. First of all, sorry, just delete this number. Okay. Now just copy this one, like okay. So you have to be careful, okay, with Ly and Lz. Okay. Okay. So so there's another thing you can look after. Okay, you can see here at the design main. Okay, main, we have 200 our allowable limit, so software will automatically check our values, KL by R ratio, whether we that is within 200 or above 200. Okay, so for flexural member, okay, for flexural member, you can bypass this KL by R ratio check. Okay, you can bypass this ratio check. Fine. Okay, if you see your axial load, okay, if you see your axial load is very less, okay, very less, then you can bypass this KL by R ratio. If you want to bypass this KL by R ratio, then what you have to do? You have to go to again, define parameters. You have to go, main, okay, sorry, main here, and just put 1. Okay, here 1 means you are not allowing software to check KL by R ratio, and then add this one. And then if you want to put assign this value to the desired member, you can put. Okay, say we don't want this rafter to be checked for slenderness ratio. Okay, then you just put this value. Then what will happen? Then software will not check KL by R ratio for these members, for these rafters. Okay, as you have bypassed, you are telling software you don't need to check for this particular rafter. So if you see your axial load is very less, okay, your axial load is very less, then you can bypass this check. Okay, because if the KL by R ratio is more than 200, then you will have to increase your size. Okay, so keep in mind that uh, okay, say okay, say your axial load is say 50 kilonewton. Okay, then and you have a I section. Okay, I section. let us consider the area of this I section is say say 1500 millimeter square. Okay, then you divided this value with the area. Okay, so the value say 33, okay, Newton per millimeter square, which is equal to ME. Okay, then you divided this 33, okay, by 345. Why 345? Because we have considered, our yield distance is 345 kilonewton per meter square. If we convert this, MPa, then it will be 345 MPa. Okay, so divided 33 by 345, you will get, okay, 0.9, which is equal to 9%. Okay, so if you see this is more than 10%, okay, if you see this value is more than 10%, okay, then you should stick with main equal to 200. Okay, if it is less than 10, if it is less than 10%, then you can put main 1, okay, for that, for any particular member. Okay, but note that this is only applicable for flexural member, only for beam or rafter, because these are normally called flexural member. But you have to check whether it is within 10% or above 10%. If it is within 10%, then you can apply for main 1 for that particular flexural member, because here you can see the flexural load is very less. Okay, if it is more than 10%, then you should stick with 200. Okay, that will be a good idea. Okay, so if you don't want to calculate like this way, then you just simply put 200. Okay, this is the most conservative method. Okay, so that's why I have I have this line. Okay, conditional. This is conditional. It will depend on the calculation. Okay, so if you don't want to calculate, just go for, okay, if you don't want to calculate, just go for 200. Okay, so this is how you can calculate and assign. Now we'll save it. Okay, so we just have to save this one. Okay, now you can see all the parameters has been set here. We are not assigning this, so we will just delete this command, delete command. Okay, let's see, delete. Okay, so this is the way you can assign the parameters to our model. You can go to the parameters section again. Here you can see you have lots of parameters, but we have assigned only few of them, because these ones, okay, govern the design and analysis of the model. If you go to the others one, they are not directly connected to design or analysis. Okay, rather they are inclined to the detailing. Okay, so these are the parameters which are very critical and which you have to assign, okay, to get a perfect result. Okay, other parameters are for detailing or for checking, or to find out something, or like this one. Okay, so this is done. You can see check code. So software will automatically check the code. Okay, so we have assigned parameters for our steel part. Now we will assign for our RCC part 2. To assign for RCC part, we have to just go to concrete. For RCC part, it's simple. Okay, go to define parameters. What we have to do? Okay, you have to assign FC prime. Okay, this value, you can see this value. Okay, this value is equivalent to 4000 psi. Okay, so you can keep it or change it according to your requirement. Okay, so I just add this one. Then you can go for FY main. This is for yield strength of reinforcement. This is 60 KSI. Okay, so you can add this one, and this is for your secondary. That means tie or stirrup. You can also add this one. We'll keep this one, and then you just need to assign our clear cover. Okay, so as you know, for column below grade. Okay, so the clear cover will be more, say 65. Okay, this one is also 65. This is clear cover for side, and this is for top. Okay, just assign this. Okay, again we go to command section. Okay, we want to design beam. Okay, design column. Okay, so go here. Okay, select all the RCC portion you can see here, and then assign. Select. You can change it, no problem, according to your design specification, and then assign it. Okay, and you can assign it again. Now design beam. Okay, so now we'll select just only beam. That means our grade beam. This is our grade beam. Okay, we will select this to only our grade beam. Okay, now the design column. So select all the columns. This one, all our columns. So column will, this RCC portion will be designed by ACI 31808. Sorry, actually 2018. If you want to 2018, you can keep it. If you want to change it, then you can go to a command file. Then you can go here, the end. You can see all your data has been input here. You can see here. Okay. Okay. What has been changed? Okay, so this is how you can analysis. Sorry, this is how you can assign your design parameters for RCC and steel portion and apply it to models. Okay, so this is a very important lesson to get the perfect analysis and design of this shed or any kind of building. Okay, so this is comes to the end. Okay, so in this next lecture we will discuss about direct analysis method. How to apply that method, we will discuss this in next session. Okay, so for the time being, keep watching and thank you. Okay.